Okay, thanks a lot for the very kind invitation. It's always a pleasure to present here, even if virtually. So, in fact, as Jonathan was saying, uh, I have been working quite a bit on machine learning for the last 6, 7 years. And this paper that I'm going to present circulated recently as an MBR working paper, or you can find it on my webpage. And it's a survey paper, it's a commission survey paper, but I think it's very nice to present because it really offers an overview of some very basic ideas. Nevertheless, also point out that if you go to my webpage and you click on teaching, you will have all the slide decks for a whole semester course that I teach on machine learning for economists, and where many of the things that I'm going to say today are going to be presented in a lot of detail. And machine learning can be used for many, many things, but today I'm going to concentrate on how one can use deep learning for solving economic models. Since we don't have a lot of time, let me assume that all of you know why we are interested in solving economic models, and let me jump directly to the meat of the argument. As I will illustrate in just 1 second, a very large class of problems in economics search for a function d that solves an operator t. That is, we find a function that when we plug it in into an operator t, we get a 0, where the 0 is not the scalar 0, is the 0 element in some functional space. As I will illustrate, as I was saying, in just 1 second, this is a very, very general formalism that allows us to deal both with a case where we are interested in solving the market equilibrium or when we are interested in solving the social planners problem. Let me illustrate this point. So take, for instance, the case that you have the very basic stochastic neoclassical growth model, and I'm going to work already directly with the social planners formulation. We have a social planners who's trying to maximize the expected discounted utility from consumption, where beta is the discount factor and E is the expectation operator, such that it can use what it produces over here and the undepreciated amount of capital over here to consume and to have capital tomorrow. And the problem is stochastic because we have a productivity shock that evolves over time as an autoregressive process with some productivity shock. It is straightforward to know that this problem is characterized by a first-order condition where the marginal utility of consumption today is equal to the marginal utility of consumption tomorrow times the rate of return on capital discounted and the expectation. Well, how is this the problem I was telling you before in terms of an operator T? Because if you search for a decision rule such that you map with that decision rule the states of the model, the capital and the productivity into 2 dimensions, consumption and capital tomorrow, what you can show is that you can take this first order condition, move the right-hand side into the left, and what you will get is this operator T, which is just the marginal utility of D1, which remember is the decision rule determine consumption minus beta the expectation, and the marginal utility of D1, again consumption, but it's going to be consumption tomorrow, which means that you need to evaluate the states tomorrow, which is D2, which is the capital tomorrow, and CT plus 1, that's okay because we are taking the expectation. And then in terms of the marginal productivity of capital tomorrow, we just plug in over here the capital tomorrow. And because we have gone over here and we have moved the right-hand side to the left, we get a functional 0. Okay, so that basically means, as I was mentioning before, that if you find this function d and a transversality condition is satisfied, and don't worry too much about that transversality condition at the moment, you are done. Okay, so remember what I was mentioning before. We are looking for a function d that plugging into an operator gives you a 0, That's exactly what you do when you take the first order condition, an Euler equation, you plug in the decision rule, and you get a 0. Well, but sometimes you don't care about a decision rule. Sometimes what you are looking for is a conditional expectation. And we go back to the same Euler equation that I had before, and now D is going to be in one dimension consumption, and in the other direction, in the other dimension, is going to be this conditional expectation on the Euler equation over here. And again, I'm going to be able to find an operator T, which is just the Marian utility of D1, the first dimension consumption, minus beta D2, this conditional expectation. Why you may want to solve for a conditional expectation instead of solving for a decision rule? Well, for instance, think about a model with a zero lower bound. In a model with a zero lower bound, the decision rule of the central bank is going to have a kink at 0, at the nominal interest rate equal to 0. That's a very difficult decision rule to approximate. However, the conditional expectation is going to be well behaved and smooth, and is much easier to approximate. Let me give you yet a third example. Associated with the previous sequential problem for the social planner, there is a recursive problem that writes the problem of the social planner as a value function that depends on the states of the model, capital and productivity, being equal to the utility today from consumption plus a continuation value function that depends on the states tomorrow. And in that particular case, the operator is nothing more than the Bellman equation. D now is going to be the value function, and we are looking for the value function such that the left-hand side and the right-hand side of the Bellman equation are equal, and then we get a 0. What these three examples share is the general point that, look, you are either looking for to solve a first order condition, or you are looking for solving a conditional expectation, or you are looking for solving a value function. And at the end of the day, all three environments share a common characteristic, which is we are just looking for a function that plugging into the operator generated either by the first order condition or by the Bellman equation gives you a 0. And the point is that I did this with the stochastic neoclassical growth model just for simplicity. I can do this for any model that you can imagine. I can do this for a New-Keynesian model. I can do this for a complex Kiyotaki-Gerler model. I can do this even for a game, you name it. At the end of the day, I'm always looking for a function D that plugging into some type of optimality or equilibrium condition gives me a 0. Very good. The reason why we have spent that much effort into setting up the problem with this formalism is that we can start thinking about how to solve functional equations using everything we know from applied math. And mathematicians will tell you that the general idea for solving functional equations is that we are going to substitute the unknown function d that we are looking for by a parameterized dn of x theta, where theta is going to be a vector with n entries of coefficients that we will need to determine. Okay? So the idea again is very simple. Is instead of looking for a function d, which is very difficult to do, we are going to look for an approximation d of n that depends on some parameters or coefficients theta. And the two main classical approaches that we can follow in economics for the last 25, 30 years are variations of this theme. For instance, what we can do is we say we are going to look for a function d, which is going to be approximated using perturbation methods. In particular, we are going to have some type of polynomials of this form, and we are going to use implicit function theorems to find theta 1. Or we can have projection methods, where what we do is we approximate the function d as the linear combination of some bases, for instance, Chebyshev polynomials. And what we do is we determine the thetas by projecting t, the operator that we're looking for, against that basis. Pretty much every simple, excuse me, Every single solution method that you know is a variation of either perturbation or projection methods. So for instance, all of you have heard about linearization or log linearization. Well, it's just a perturbation method where n over here is equal to 1. You have heard about linear quadratic approximations to the utility function, which is actually nothing more than a first-order perturbation. You have heard about parameterized expectations. It's just a particular form of a projection method. You have heard about value function iteration, which is nothing more than a projection method. Or you can think about policy function iteration, which is basically value function iteration slightly done in a slightly different way. But the point is, all the class of methods that we have been doing in economics for 30 years is a variation of a common theme. We take a function d that we are looking for, and we approximate it using either perturbation or projection methods. Well, there is an alternative, and that's why deep learning plays a role, which is to say, well, instead of using either perturbation or projection, what I'm going to do is to approximate the function d by a neural network. And that's why now I'm going to have a new parameterization and a new notation d of nn. And over there, what I'm going to have is the following. I'm going to approximate the function with a leading term, that's not a big surprise, a constant theta sub 0, and then I'm going to have a linear combination from m equal to 1 to capital M, where theta m are going to be the new parameters, the new coefficients of phi zm. And what is phi of cm? It's going to be an arbitrary activation function, which we will see later is going to be extremely simple. So don't think about complex activation functions. We are going to be thinking about extremely simple activation functions, like very simple senoids, for instance. And then Zm is going to be a linear combination of the different elements of x. X in general is going to be a vector, and we are going to take the different elements of x and find a linear combination of them. So what are we doing here? Basically, what I'm doing is the following. We are saying, look, we take the original characteristics of the problem. This, in machine learning, is called the features of the data. But in the context of solving economic models, the features of the data are the different states of the model. So for instance, in the case of the stochastic neoclassical growth model, is going to be capital and productivity. Okay? So the X are the features of the data, capital and productivity. And what we are going to do is we are going to take a linear combination of capital and productivity over here. And we are going to bend that linear combination using phi. And that's going to be known as the representations of the data. Now, be very careful, because data here does not mean data like inflation and unemployment in the real world. Data here means the states of the model, okay? It's the data of the problem. Now, what we are going to do then is basically do this capital M different times. Of course, notice that the coefficients over here, theta and m, depend on m. Okay, so we are doing this for m different combinations of coefficients. And depending on how large m is, when m is small, we call this a thin network. When m is large, we call this a wide network. And the point is that we are going to select the theta here, the thetas here, and the thetas here, such that this approximation d and n is as close as possible to d of x, given some relevant metric, like for instance the L2 norm. So the idea is very simple. Is again, I'm looking for a function d of x, where x are the states of the model, and I parameterize that function as a neural network. Let me give you a graphic representation of what we are doing. We are basically looking at the different inputs, which are going to be, remember, in this particular case, the states of the model. We are finding some weights, we are finding a linear transformation, and then we are activating that linear transformation with this activation function phi. So let's compare for a second this approximation we have just come up with the standard approximation you will have with Chebyshev polynomials. So remember, Chebyshev polynomials is just a particular example of a projection method over here. And what you are going to find is that they look surprisingly the same. You have a leading term in the neural network approximation, and you have a leading term on the Chebyshev polynomial approximation. And then you have a linear combination from m to 1 to m, depending on how many activations of the data you have. And over here, you also have a linear combination of the different Chebyshev polynomials. What changes is in the phi. In the phi, we are just going to take a linear combination of the features of the data, which remember are the states of the model, and we activate them with the activation function phi. While in Chebyshev polynomial, we are going to use the Chebyshev polynomials over here. Remember, they are indexed by m over here. So what we are basically doing is introducing a lot of coefficients over here that do not appear over here, but in exchange, we only have one activation function, while with Chebyshev polynomial, we will have m different polynomials. But if you look at these two, you realize there is nothing much particularly deep or surprising or new. It's just changing this for this. Now, you are probably asking, why does this work? Why is this a very clever idea? Why do we want to substitute the Chebyshev polynomial over here by this very simple activation function over here, but on the other hand, have these linear combinations inside? Well, because basically what you are doing is you are applying a number of change geometric transformations. Strictly speaking, what you are doing is you are looking for a convenient geometrical representation of high dimensional manifolds. You can show carefully, and if I had a little bit more time, I could go over the theorems, that by doing these linear transformations and then applying this activation function, you are actually finding a very convenient geometrical representation of the problem. Let me give you a very simple example that you already know in economics. Imagine that you want to approximate a Cobb-Douglas production function like this one that depends on capital and labor. We all know that in levels, approximating this function is difficult. However, in logs, it's surprisingly easy. What have we done over here? We have moved the representation from being in levels to being in logs. In general, we don't know how to do this. We don't have enough knowledge about the properties of the data, which remember are the states of the model, to do this transformation. So what we are going to do is we are going to use these linear transformations and these bendings through the activation function to do that, or to find that representation for us automatically by selecting the phis that, as I was saying before, get you as close as possible to D. A standard way to think about it is a famous example of unwrapping a three-dimensional ball. Imagine that what we want to do is to approximate a ball of paper like this one. That's just a function approximation problem like any other, except that it's extremely complex because a three-dimensional ball is very, very convoluted with all these ridges and irregularities. In fact, the real situation is even worse because you are dealing in a very, very high dimensional space, models that have 10 or 20 or 30 state variables. And what you're going to be doing by taking linear transformations and the activation function is nothing more than unbending the paper and getting back to a very simple linear Euclidean space. And again, as I was saying before, if I had a little bit more time, I could show you the theorems where we carefully make the argument that that can always be done, and the theorems are stated and argued for in my slide decks online. But the point is, doing this instead of this is a very clever idea because you are moving the problem from a difficult geometric representation like this one or like this one in levels to a much more convenient geometric representation like this one or this one in logs. Okay, very good. So once we have introduced the basic idea of a neural network, we can ask ourselves, what is a deep neural network? And a deep neural network is a network that does what we just did, but several times. So deep over here is in terms of depth, like if you are digging a hole in your backyard. It's not deep in the sense of sophisticated or complex or subtle. So what we are going to do is, again, as before, we take the features of the data, we take linear transformations, and with these linear transformations, z of 0m, we plug it over here, and we activate it with an activation function, and we do it m super 1 times, and we get a new representation of the data. And then we take that representation of the data, we put it in an activation function, we take combinations of it, and we put it in another activation function. And we do that j times. So it's exactly the same that we were doing before over here, where we take the features of the data, we take linear combinations and we activate them, and then we take linear combinations again, except that we are going to do this one time and again and again and again and again until we do it j times. So as I say over here in this bullet point, what we do is we continuously create new representations of the data by composing older representations. And of course, in every step, the activation function can be different, or the number of times we do this, the m super 1 or the m super 3, can be different. Although in practice, usually you do it in the same way. And this is the type of graphic representation that you probably have seen many times. You take the features of the data, again, as I was saying before, capital and productivity, you combine them and you activate them. And then you do it again, and then you do it again until you get to the end and you get the final output. So the question now is a little bit harder to write down the comparison with Chebyshev polynomials, but it's still basically the same thing, except that over here, instead of being just the features of the data, is the representations of the features of the data, is the representation of the representation of the representation of the representation of the features of the data. But at the end of the day, it's nothing more than a very simple parameterization of the function d that we are trying to approximate. You are probably wondering at this moment, why are we doing this? Why do we want to do it several times and then get a deep network instead of just having one network? Well, this is one of these very interesting situations where we first discovered that this works, and only later on we started understanding why it works. So let's follow what actually happened in reality. There was something called ImageNet. ImageNet was a competition that existed a couple of decades ago to identify breeds of dogs from photographs. So there was a set of photographs, and some photographs, it was a German Shepherd. In another photograph, it was a Bulldog. In another photograph, it was a Dalmatian, etc. And the competition was that you had to submit some type of machine learning algorithm that will be faced with these photographs, and the machine learning had to classify correctly the breed of the dog. And this was a complex problem because photographs can come in many different shapes and many different shadows, etc. And the winner for a long time was a shallow neural network, which, remember, is nothing more than a very basic neural network with only one layer, with only one step. I forgot to mention that each of these steps over here sometimes is called a layer. And the error that you had around 2010 was 28%. That means the computer will get it wrong, will get the breed of the dog wrong in nearly one of its three occasions. And there was a small improvement over time, by 2010 and 2011, we went from 28 to 26%, but it was still the case that we were not doing fantastically well. And then, all of a sudden, AlexNet, by a group of researchers in Canada, does the following. They say, let's move from a one-layer neural network, which is what people have been doing for 50 years, into having 8 layers. There was no particular deep reason, and if you read the paper, it was basically, let's try to see if this works. And to everyone's surprise, we went from 26% success rate to 16% success rate. And in the field of image recognition, this was a drastic increment. No one had ever seen an improvement in accuracy of this degree in just 1 year. Well, once we figured it out that 8 layers work better than 1 layer, researchers immediately jump, you can see next year, to 8 layers still, but 2 years later to 19 layers, 22 layers, 152 layers. And by the moment we are in 152 layers, the error was 3.6%, which is actually below human error. So if I give you photographs of dogs, the average human is going to do a little bit worse than 3.6. And in some sense, it didn't make much sense to continue with this competition any longer because we had pretty much achieved perfect ability to classify. And this is why when everyone asks me when was the birth date of the modern artificial intelligence revolution, I always say 2012 with AlexNet. This is what started everything. And after AlexNet, and if I had a little bit more time, I could tell you a little bit about the history of the field. People realize we can do all sorts of things with multiple layers. Then a variation of the multiple layers is going to be the idea of a transformer, and that's behind the large language models that all of you use. But at the end of the day, a large language model is just a deep neural network. And that's why in 2012, the world changed, even if we did not realize that at the time. But then, of course, mathematicians and computer scientists went back to the whiteboard and asked themselves, why is the case that having multiple layers work better? And very soon they realized is that the number of representations that we have increase exponentially with the number of hidden layers, while the computational cost only grows linearly. Let's go back to this graphic representation. As you have more and more of these layers, you are going to have more and more of these different representations of the data, the Z's that I'm building in each step, and this grows exponentially in the number of layers. But however, the number of floating point operations that you need to implement these transformations, which remember are just nothing more than fine transformations and bendings by an activation function, grows only linearly. That means, as I explained in the slide, that we can induce incredibly nonlinear behavior without the need to know much. Domain knowledge is just your understanding as an economist of the problem that you are trying to approximate. And deep neural networks then are going to be enormously efficient in unwrapping this ball. You can think about this ball as the representation of the data that depends on capital and productivity. And this is the representation of the data that depends on some transformation of capital and productivity. And in the same way that we are moving from level to logs over here. And what the deep neural network does is unwraps the paper like this. Of course, once you have these complex representations of the data and you solve the model, that doesn't imply that when you are, and I mentioned this because last week I was given a keynote address at the Bank of Spain and I realized a couple of people missed this point, doesn't imply that you are going to report the results in terms of those complex representations of the data. No, once you have solved the model, once you have, for instance, find the value function that encodes the dynamic problem of the social planner in terms of complex representations of K and ZT, you don't report the data like that. You just undo the transformation, but that's very easy. The difficult thing is to find V in the right representation, but once you have found V in the right representation, undo it, and coming back to the original representation is trivially easy. And we do that in math all the time. In math all the time, we work in the right space, we solve the problem in the right space, and then we come back to the original problem. Think about in algebraic geometry. We have a geometric problem, we set it up as an algebraic problem, we solve it, and then we come back to the original geometric representation, which is what we care about. So that's why neural networks, deep neural networks, became so immensely popular, because they really, really do work better at finding very complex representations. Now, that means that you can prove a lot of important theorems. And again, unfortunately, I'm very short in time, so I can only sketch what those theorems are. For instance, you can show that neural networks are universal approximators. They allow you to approximate a very large class of functions, including functions that have jumps, non-differentiabilities, etc. Neural networks also break the curse of dimensionality by unballing this complex ball into just a simple Euclidean space. We are working in a quasi-linear environment, which means that we can solve problems with dozens, hundreds, even thousands of state variables. Now, it doesn't imply we can solve every single problem out there, but it expands in a completely drastic way the type of problems that we can solve. I don't know how many of you have tried to solve a Chebyshev polynomial approximation with more than 3, 4, or 5 state variables, but it's really very, very difficult. Solving those problems with neural networks is much easier. But more importantly, even than the theorems, from a practical perspective, neural networks are very easy to code. Last week, I was lecturing at the European Central Bank, and we went in detail over the code that I use to compute a neoclassical growth model. It's 93 lines of code, and I emphasize the word 93, the number 93, because if I try to solve the problem with any other method, the lines of code will be much more, will be at least 200, 300, 400. The code is very stable and is very scalable for multiprocessing. And that's why, remember, we are basically building these neural networks around tensors, and that's why NVIDIA is the most valuable company in the planet, because NVIDIA produces the massive processors that are perfect for neural network processing. There is also a
Jesus?
few other... Yes.
Yes, we have a question from Yosiachin.
Yes.
Thank you. So I have a question about how to treat the solution. The way, if I understand correctly, the way you presented it, the way the problem was set up was similar to the standard approximation, and you made the parallels between the Taylor approximation and the neural network.
Yes.
So if it is an approximation,
yes.
Now, so how should we treat the solution? Is it like an exact solution because the M there, right? It parallels to the order of approximation of a Taylor approximation, if I got it right?
Yes.
And so is it like an exact solution, or is it an approximation? And if it is an approximation, around what point can we analyze large shocks using it or not?
Okay, so
thank you.
So yes, it's an approximation, exactly the same that when we are doing perturbation or when we are doing projection, but maybe the point that is important to remember here is that it's a global solution, it's not local. Okay, so in that sense, that's why I was comparing it over here with Chebyshev polynomials. Chebyshev polynomials are also a global solution. It's a solution that is not accurate around a neighborhood of a point. It's a solution that is accurate in the whole domain of the state space.
Right.
So
Like
in
a
that
value
sense,
function iteration, if I got it.
exactly.
Okay,
And now,
okay,
of
got it.
course,
Thank you.
it's an approximation, and something you can always do is evaluate things like Euler errors, etc. And that's in fact how we are going to show you in a second. We are going to train the neural network. Thank you
Got
for
it.
your
Thank you.
question.
And we have another question from Victor Marinkov.
Yes, thank you, Jesus. Can you hear me?
Mm-hmm.
Yeah, just a very quick one. I think I understand some of the benefits of neural networks compared to traditional methods. I was wondering, are there any downsides?
The main downside is that setting up a neural network and running with it, if you are going to be working in 1 or 2 dimensions, is probably not worth it. So most economists are very used to write a value function iteration or a perturbation. And if you are going to work in 1 or 2 dimensions, that's very easy and very fast. And we have a lot of accumulated knowledge about it. So if I were going to solve a problem with up to 3 dimensions, I will probably still do it with value function iteration or with a perturbation. For more than 3 state variables, I will definitely use a neural network. But
I will suppose if nonlinearities are a big concern,
yes,
then
the nonlinearities are very, very, very big. Having said that, I think that neural networks have become so popular in the applied mathematics and computer science that I see a scenario in 10 years where they are the default solution method in economics.
Right.
Except perhaps perturbation. The good thing about perturbation is I can write a dinar code in 5 minutes for solving a lot of models, while neural network will take me a little bit longer.
Right. So it's all. So you're saying in terms of computation, in terms of precision, flexibility, and so on and so forth, neural networks win. And then the question is, what about the human time?
Exactly. So I will say that at this moment, I will not. I don't think I'm going to. I'm actually seriously thinking about not teaching Chebyshev polynomials anymore. I don't think there is much of a case to learn Chebyshev polynomials or finite elements, because those are the type of methods that we use for very complex problems. And I think that in nearly all these problems, neural networks are better. I will still teach perturbation because doing a Taylor approximation is so easy and so fast, and in many, many cases is all that we need. But Chebyshev polynomials, I'm seriously thinking about not teaching them next year.
Thank you.
And the last thing, which is probably also related with Victor's question, is the fact that neural networks are fantastic because you have great libraries. And over there, let me point out to PyTorch, this one over here. Okay, so if you want to learn one and only one library to implement neural networks, learn PyTorch. It's the standard in the industry, and what you will realize is that you can solve a lot of problems using the library, because most of the hard work, for instance, in terms of the optimizer that you need to implement, in terms of the definition of the neural network, etc., PyTorch will do everything for you under the hood. And also, as I was mentioning before, the fact that we have dedicated hardware, in particularly the GPUs, but also other things like TPUs or FPGAs, is going to imply that neural networks are going to keep an edge for the area. So you can have a great approximation. Imagine that you invent your own polynomial class, which may have like some fantastic properties. But at the end of the day, what you'll find is that you don't have the software and the environment to work on it, it's not going to really be a success. And neural networks have this whole ecosystem that has become incredibly large just because they are so important out there in real life applications. Okay, so I want to show you how to do this in real life. And what I have over there is code. So you can actually play. And I will share this slide with Jonathan if he doesn't mind. So you can actually click on these links. You will see code to solve a linear quadratic optimal control problem. You will see code to solve a neoclassical growth model. You will see code to do the same but in continuous time. Neural networks work both for continuous and discrete time. You will see code to solve a very large overlapping generations model. And you will see code to solve a Krusell-Smith model and a model also with heterogeneous agents and financial frictions. But what I'm going to try to do over the last minutes of my presentation is walk you through an extremely simple example, okay? Coming back to your question before, Victor, this will not be probably a case where I will use neural networks in real life because it's so simple that I can solve it in Dynar. It will take me 10 minutes to code and a fraction of the second to run. There is a very good pedagogical example to educate you about how to use this. And it's exactly the same stochastic neoclassical growth model I showed you before, except that now I'm going to do it in terms of the market allocation and not in terms of the social planner. The only reason I'm going to do it in terms of the market allocation is you can see a little bit how it can be done with markets, but adapting the example to the social planner is straightforward. So remember, as I was saying before, that the states of the model are capital and productivity. And to save a little bit on notation, let me switch to the recursive notation. So I'm not going to use a sub-index. And when I have a prime, it means the next period. And exactly as we did before, what we are going to center our interest is in the Euler equation. And I'm going to here also already specify that we have the log of the utility function is a log, just to have a little bit more concrete example. And then you have that one is equal to the expectation of beta, the discount factor, the ratio of consumption today over consumption tomorrow. This is just the marginal utility tomorrow, and the marginal utility of consumption today will be on the left-hand side, but I have put consumption already over here, and then we have the marginal productivity of capital over here. And I have that consumption is just equal to the resource constraint minus what we invest. That means that the law of motion conditioning, imagine that I come up with a policy for consumption and for capital. So I'm going to be looking for this decision rule for capital, conditional on this decision rule of capital. What I'm going to have is this law of motion for the states, where the first dimension is just the policy function and the second dimension is just the law of motion, the exogenous law of motion for productivity over here. Okay, so what I'm going to do is the following. I'm going to say, let me approximate K prime, the decision rule for capital, with a deep neural network. And now I have this theta as a sub-index to denote that is the approximation. That is going to belong to a particular architecture. Since this is a short presentation, I didn't enter into the discussion of what is known as architecture design. Architecture design is selecting the number of layers that the neural network will have, the number of neurons per layer, the M's, the activation function that we pick, and so on and so forth. All of those are discussed in a lot of detail in my slides online. But let's suppose that we have already done that. And then what I'm going to do is I'm going to define the Euler equation error. The Euler equation error is just the left-hand side of my Euler equation minus my right-hand side over here. So this will be 1 minus. Why do I have over here a sum? Because I'm substituting the expectation by a quadrature. And this m, sorry, I just realized that this is not the best possible notation because this m is not the m as before. This m is the number of quadrature points and omega sub I are the quadrature weights that approximate this expectation. Okay, so maybe a better notation will be, I don't know, p for p quadrature points. And then I have over here exactly what I had over here, except that every time you see a k prime, I have put k prime of theta, which is my neural network. And what I'm going to do is I'm going to find the coefficients for the neural network, the weights in the neural network theta, that minimize this Euler equation error. Now, how do I do that? Well, what I would like to do is to minimize, to find over here, you can see this argmin, the expectation of these Euler equation errors over the true population distribution. Remember, this depends on x. This Euler equation error is a function because it's a different value of the function for every value of the states. I will have, when capital is 3 and productivity is 2, I will have a different Euler equation than when capital is 1.9 and productivity is -3. So what I want to do is to take an expectation of this loss function over the ergodic distribution of capital and productivity. That's what I'm calling over here the population distribution. And this is what makes the problem of deep learning a little bit different than in engineering or natural sciences. In economics, this population distribution, the distribution of capital and productivity, is endogenous, is an equilibrium object. Because how much capital we are going to have in equilibrium depends on the solution of the model. In engineering and natural sciences, that's typically exogenous. They say, well, there is some data generating process in the real world that generate the population. For us, it's not an exogenous data generating process, it's an endogenous one. So how are we going to do it? Well, what we are going to do is we are going to try to come up with some approximation to the distribution that we don't know. And we are going to do it in an iterative way. If we come up with an approximation to the distribution, the only thing we need to do is to substitute that expectation by a sum. We draw from the distribution, and we just minimize the average of the draws of over the distribution of the loss function. And in particular, what we are going to do is the following. And this is what the contribution of my papers have been. We are going to sample from a misspecified population distribution. Remember, we don't know this distribution. This distribution is an endogenous object itself. But what we can do is the following. I start with some assumption about that distribution, and I sample from it. And I periodically generate new sample points using the new function that I have estimated or that I have solved. Okay, let me say it carefully. Imagine that you have an initial guess for what the policy function for capital is over here. So what I can do is I generate, let's say, 1,000 times, 1,000 observations from that distribution, and I train my neural network on those 1,000 samples from the distribution. And then I use my neural network to generate 1,000 points from the population. Remember, my neural network is the evolution of capital, so I can use it to generate simulated draws of capital. And I generate another 1,000. And then I retrain my neural network on the 1,000 simulated paths. And I have a neural network, a new neural network. And then I do it again. And I keep doing that until convergence. If you remember Crucell-Smith, if you don't remember Crucell-Smith, do not worry. But if you know Crucell-Smith, this is exactly what you do in Crucell-Smith. In Crucell and Smith, you postulate a law of motion for the average of capital, you simulate, and then you re-estimate that law of motion, and you keep doing it until convergence. So over here is exactly the same as before, except that you do it in terms of the neural network. For instance, for this very simple model, my first distribution of the data is from a solo model with constant saving rate, which I can solve by paper and pencil. We teach this to the undergrads. So I generate 1,000 observations from the solo model. And then I train my network on those 1,000 observations. And then I generate more data from the neural network. And then I retrain the neural network, and I keep doing this until convergence. And this is what I do with 1, 2, and 3. I hope everyone can see that point. I'm not going to get, since I'm running out of time, I'm not going to get into the numerical details about how we do it. It's extremely simple, and you can see it takes 1.2 seconds using a CPU of my laptop. Okay, so I'm not talking here about something that takes hours and hours. I'm talking about something that takes 1.2 seconds. And this is the initial versus final trajectories of capital. Of course, why is capital like this? Why is this evolution of capital over time so wiggly? Is because, remember, this is the stochastic version of the neoclassical growth model. You have positive and negative productivity shocks. But once you have converged, you still have those positive and negative productivity shocks, but you can see here the dynamics of the model have clearly stabilized. This is the initial condition, so we very quickly travel towards the ergodic distribution, and over here we are in the ergodic distribution. And you can see that the errors, once I have converged, they are trivially small. Okay, these are the initial errors of the model with the solo growth model, the solo distribution, but then I converge very, very quickly. Now, I'm going to skip the models with heterogeneous agents because I don't have time, but over the slides, I tell you how to apply these very same ideas to the model with heterogeneous agents, but very, very quickly summarizing the main message of the paper. Take your model, write the equilibrium or the optimality conditions associated with it. It can be an Euler equation, it can be a conditional expectation, it can be a value function. Substitute the function within these objects that you are interested in, like the policy function in this case, or the value function in a Bellman equation, by a neural network. And train the neural network, which means getting the parameter values by simulating from an initial guess for the model, train the neural network on that initial guess, generate new data from that trained neural network, train the neural network on the simulated data, and keep doing this until convergence. And if you are going to use a model library, like JAX or PyTorch, this can be done in a few seconds. The code will be very simple. Coming up, or something I forgot to say, coming up with an initial guess tends to be very easy. You can use, for instance, over here, the solo growth model, which is trivial, but coming back to some of the examples you asked before in a question, you can always sort the model using Dynar up to first order and use that solution up to first order as the initial guess, and you do it until convergence. And if you want to go in detail about how to do it, over here you have 5 different cases where you can look at the details of how to implement it. And as I was mentioning, this requires, like every new technique that you are going to learn, to get familiar with it. I'm not going to claim you are going to get up to speed in 10 minutes. It will require a little bit of effort, of course, like every single technique, but you will realize soon why everyone in the industry, in computer science and in engineering is so excited about neural networks, because this simple procedure that I'm outlining over here in slide 26 is really very general, very robust, and surprisingly easy to code. And I went 4 minutes over the limit that Jonathan gave me, so I apologize. Let me stop here.
Fine, thank you. Thank you very much, Jesus, for this fantastic presentation. So please raise your hand for any questions. I have one question. I have more, but just one for the moment. Is I did not hear you about talking about the data. So you presented the data. So how do you include? Yeah, how do you include time series? How do you include for approximation? I understand your simulations and these things, but maybe when you will put more data, then the estimation time will be higher than the 1 second you had. And also the subsidiary question is which package would you recommend to estimate a nonlinear model with your methods and with data?
Okay. So first of all, thank you. Those are great questions. So first of all, let me highlight that today I was focusing on solution of methods. Okay, so I was just saying, you have a model, you want to solve it. Now the issue will be how you can take a model like this to the data. That requires a little bit more extra slides, because basically once you have your solution, so for instance over here you have solution, your value function, you will need to build a likelihood around it.
Yeah.
And that's what you will need, for instance, something like the particle filter that I have used in the past myself. All the details about how that can be done, I have a student. Let me see if I can find, and hopefully I don't have anything embarrassing in my no, I only have responses to the editor. Okay, so that's good. But one of my very, very best students, Leonardo Melosi, who is now a professor at the European University Institute, has a fantastic paper, this one. Oops, got it. Yes, estimating nonlinear heterogeneous agent models with neural networks. And that will be kind of the natural next step after I have told you today. Okay?
Excellent. Thank you very much. It's very helpful.
Invite him. He's fantastic. And, he has been trained by me, so he knows this stuff well. Second, if you are interested, remember in more of these things, I mentioned just put my name. The good thing about my name is I promise I'm the only Fernández-Villaverde out there. You click on teaching, and over here you will see machine learning for economists.
Yeah.
You have over there a whole semester. And if you are just interested in data analysis, not in structural models, over there machine learning for data analysis will give you everything. And also over here in coding machine learning algorithms, you will learn about the different choices of programming languages, libraries, etc. Now, quickly, my favorite one is PyTorch. It's open source. This is, I will say, the most popular library right now. It's very easy to learn. It's for Python, but if you are not a Python user, it's relatively easy to hook it with MATLAB or with C++ or with Julia. But PyTorch is really a state-of-the-art. It's a fantastic library. Now, in my example, I use JAX, which is not this very scanty dress lady, but JAX library Python. Okay, over here you have it. Okay, JAX, no, but that's not the one I'm looking for. JAX, okay, over here. JAX is very nice. I will say in terms of power, it's more powerful than PyTorch. It's also a little bit harder to understand. It uses functional programming, which if you come from computer science, it's something very natural to you. If you come from economics, it's a little bit harder, but you guys in Israel have great programmers, so I'm pretty sure you probably have someone around the bank that knows how to use functional programming. Okay?
Yeah.
JAX, again, as I was saying before, is more powerful. It's a little bit harder to learn how to use. That's why, by default, I recommend PyTorch. But both PyTorch and JAX will be outstanding choices. This is a little bit if you were asking me, should I buy a Mercedes or should I buy a BMW? Look, both Mercedes and BMW are great cars. You are not going to make a mistake going with any of them. Okay.
Thank you very much. So we have a question from the chat, and then we will switch to the questions in the video. Just to inform the attendees that the links you mentioned in your slide are already available in the website of your seminar.
Yes.
So we have a question from Fluvio Radi in the chat, who is asking, why are we sure to always convergence, and does it come from the universal theorem?
Okay. So this thing over here, given that this mu star is endogenous, we cannot warranty convergence. Unfortunately, the universal approximation theorem assumes that you know the mu, while over here we are solving both for the policy function and the mu simultaneously. So yes, you can find situations where you do not converge. In practice, I don't think this is a very important concern, and I think you could prove it. So if anyone is interested in writing that paper, I think you will be able to prove that argument, that you actually have a fixed point where you do converge. But at this moment, we do not have a proof that you converge both in K prime and in mu. The universal approximation theorem tells you that given mu, you will converge on K prime, but not that you will converge in both at the same time. That's a fixed point problem. That's a bit harder to prove.
Excellent. Thank you very much. So we have first a question from Maurice Scheidenberger.
Thanks. Yeah. I have a rather practical question, maybe, because if I would imagine myself solving, let's say, more complex models than the standard ones we've seen using this method. Previously, if the solution method I have in mind fails, I feel like I can look under the hood inside of the code and see maybe where things go wrong. Here, yeah. I mean, I cannot look what happens inside these networks. And so I wonder if the skill set to solve these models moves a bit more towards machine learning. And maybe if this is true, and if you have a reference to suggest kind of for someone getting into this, where to find the practical tips of making the solutions work.
Yeah, so people ask me that question a lot of times, and I think it's a little bit, it's not, I don't think that deep learning is more of a black box than Chebyshev polynomials. It's just that you have experience with Chebyshev polynomials, and then you know where to look for failures. Well, you may not have enough experience with deep learning, and then you don't know where it breaks down. It reminds me, if I can make a joke, of that Portuguese that goes to France. This is an old joke from the 18th century, and say how smart French are. That, you know, I have been all my life trying to learn French, and I'm still struggling with it. But in France, even 4-year-old kids speak French. So the point over here is that machine learning is not a black box. You can debug it, and you can look at why the model is not working. You can look at the problems of the approximation exactly in the same way that you can do it with Chebyshev polynomials, with Taylor approximations, with value function iteration. Is that you need to get used to look at slightly different places, and you need to learn the test to do that. Unfortunately, I don't think anyone has a terribly good tutorial to do that. My experience is that if you try to look on the internet, on YouTube, or just Google, you are going to find pieces here and there. But that's one of the reasons I have been thinking about maybe writing a book about this, is precisely to provide a lot of that details about how to implement this in practice that I cannot publish that in a paper. If I send that to the journal, the editor with good reason is going to say, oh, I don't want to publish those kind of small little details about, you know, how you do this or how you do that. My hope is that as the profession evolves over the next 5-6 years, we will gain that knowledge and it will become very straightforward to do it. But it's, yeah, I give you the point. There is a little bit of know-how that at this moment, if you're an outsider, it's a little bit difficult to get at. But it's feasible. It's not, and if this was a little bit of the longer version of this talk or my semester, I think that by the end of the semester, the students are pretty good at that.
Thanks.
Thank you. So we have another question from Victor Marinkov.
Jesus. So I work on expectations and learning in macro. And when I see this machine learning and the algorithm behind it, it kind of reminds me of how a learner tries to figure out the aggregate law of motion and the model. So I was wondering, is there any work recently looking at how perhaps this can tell us about expectational frameworks and deviations from rationality?
Yes, exactly. So what I did today, no, that's a fantastic question, Victor. So what I did today is to say, well, we have the model. It's a full information rational expectation model, and I'm going to look for the solution, the equilibrium solution of the model. But you can also give it a slightly different spin, which is to say, well, these are really learners. When I'm given the household, this neural network is very similar to what we are doing in learning in macro. And there is a lot of people pushing that interpretation. So for instance, let me tell you about a fantastic paper. No, the problem is, unfortunately, he, in the same way that I have a very, very odd last name, he doesn't. It's quite.
I think he's written with a Y.
Yes, with a Y. Okay, let's do the following. Zurich deep learning. I hope he forgives me for. Okay, fine. I cannot find the exact name, but I have another paper over here that maybe will help. No, 1 second. Well, anyway, Yu Cheng has a very nice paper with Ben Moll. He just presented it at Penn, maybe this one. Oh, for instance, this is another good paper. So this is by Federico Gabriele at Sapienza, Aldo Glienne at Bank of Italy, and Marco Taboga. And it does exactly what you're suggesting, which is to think about this type of learning. When you are doing this kind of, you learn within the model and you are really thinking about the agent learning in the model, is what sometimes is called as reinforcement learning. And again, in my slides, I have a slide deck on reinforcement learning. And in this paper, they teach you a little bit how to do it. And you can see over here how they actually do it. And it converges really very nicely. And it has this behavioral / learning interpretation. And then there is also this paper I was mentioning before by Yu Cheng and Ben Moll. He presented it at Penn last week or 2 weeks ago, and it's very similar in approach, and it's a great paper. And that's exactly what you're suggesting. So I strongly encourage you to take a look at those 2 papers.
Will do. Thank you so much. Thank you.
Thank you very much. So if we have another question from the attendees, feel free to raise your hand. I have another one, which is more central bank oriented. Sorry for this.
Of course.
But do you think, would you recommend central banks and research departments at central banks to recruit data scientists that are closely working on these fields? I mean, okay, data scientists are working with data, but do you think we should, or central banks should recruit people who are specialized in Python and in solving such problems?
Yes.
In central banks, I mean.
Yes, so I think so. I think this is important. And I think now, in that, and I know, for instance, because I have worked quite a bit with the Bank of Spain and the Federal Reserve Bank of Philadelphia, and that has been, I'm a scholar in both places, and that's exactly what we have tried to accomplish. Now, it needs to be the right profile in the following sense. You want someone that ideally knows a little bit of economics, maybe someone with a double undergraduate degree in economics and data science, or someone who, for whatever the reason, pick up a little bit of economics along the way, or in case that you don't find anyone with that profile, someone who is willing to listen to economists. and the reason I say that is this simple point that this mu star is endogenous is a very subtle point. And talking with, I tried to write a paper once with a very, 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 very famous computer scientist. And look, he's probably way smarter than I am, but he was a computer scientist. He has been working in computer science for 40 years. He just couldn't get the fact that this star meant that this distribution was endogenous. So what I will try to do is search for people who are willing to listen to us as economists and are willing to understand that those distributions are endogenous. That yes, we are going to learn a lot from computer science, but that our problems are slightly different and that they are open to consider why our problems are slightly different. But I have found that people with good backgrounds in computer science know how to write code that is way better than mine. I had a great student, Wen Zhao. She's at Tsinghua University. She did her PhD in economics with me, and she's a computer scientist as an undergrad from Tsinghua University, which, as you probably know, is probably the best engineering school in China. And I will give her my code, and she will come back the next day, and I will look at the code that she kind of improve over my code, and I will be, oh my God, it's not even close. Her code was so much better, so much cleaner, so much more efficient. And I'm not a bad coder myself, let me put it in that way. And so yes, if you find someone who is really an expert on some of these things, is a great addition to the team. But as I was saying before, is someone who needs to be willing to understand that you are going to be working in a multidisciplinary team, and the way we do things in economics, and I think with good reason, is sometimes a little bit different than the way we do things in engineering or in natural sciences.
I see. Thank you very much. So again, if you have any questions, please raise your hand. I have my last question. That is, so I started my PhD with DSG models and the DINAR, and so I would really want to have your opinion about how do you see the future for these programs, this package like DINAR and Julia. Do you see a future, or do you think the future is more on PyTorch and deep learning solving?
No, I think we are going to move into a future where there are going to be different approaches. So if you ask me, I have my very basic neo-Keynesian model, and I want to understand how the model works. I want to kind of solve it quickly. I want to have a reasonable first order approximation. I think that DINAR is still going to be a fantastic approach to do it. Okay. So imagine, your boss, Amir is still the boss. So yeah. Amir walks into your office and Amir says, oh, I want you guys to look into this, a small variation of the neo-Keynesian model with this small theme that I find is very important for us right now. And I want you to tell me tomorrow at 9 a.m. And I know that at central bank, this is often the case. So yes, I will take my neo-Keynesian model, I will write the small modification that Amir has asked, I will compute it with DINAR, and I have a nice and probably 90% accurate solution in 24 hours. And for a central banker, that's a lot of times all you need. But sometimes you may want to do something much more sophisticated. You say, no, this is not about that small modification of the neo-Keynesian model. I want to think about a model where there is a very complex network structure, not network structure in the sense of neural networks, but network structure in the sense of global supply chains. and the global supply chains are deeply disturbed by a very large shock, like a conflict or some, trade war, and I want to very carefully trace the consequences of that. And then you use a deep neural network. So my view about computational models have always been that sometimes you feel like fish, sometimes you feel like meat. And the fact that you like a nice fish dish doesn't imply sometimes you don't like a nice meat dish. And that's really how I think about solution methods. I'm not militant about any of them. I think they are nice tools. Joan Robinson, the great British economist, talked about economics as a toolbox, and I think that what distinguishes a great economist from other researchers is that great economists understand which tool is necessary for each particular problem at the time. So yes, I'm in the DINAR board of directors, and I think that DINAR will still be around in 5 years.
Excellent. Thank you very much. So if we don't have any additional question from the floor or attendees, I want to thank you very deeply, if I may, for this fantastic presentation and new horizons that you presented today, and wish you a lot of success with this new field of research you are opening to us.
Okay, and thank you very much for this very kind invitation. And hopefully we can do this in person one day soon.
I hope to. Yeah. Have a nice day. Thank you very much.
Thank you. Thank you,
Jonathan.
Thank you, everyone.
Thank you. Bye-bye.
Bye-bye.
Thank you.
Bye-bye.
Bye.